Okay, so let's start today's lecture. Last time we were looking at a two-body problem where we had two particles of mass m1 and m2 which were interacting via a central force, okay, which we said is given by a potential energy function u of r. Okay, so m1 and m2 interacting via potential energy u of r. Okay, and the fact that it depends only on the separation distance, the magnitude of the separation, makes it a central force. Okay, and then we saw that we could reduce this two body problem to a one body problem. Okay, so we reduced to one body problem, and we wrote down the Lagrangian as L equals half mu, where mu is the reduced mass of the system. Okay, r vector dot square minus u of the potential energy which you had originally in the problem. Okay, then we imposed conservation of momentum, angular momentum. Okay, and by using only the fact that conservation of L implies two things. First, that the direction of L is going to be fixed, it is not going to change, and second, that the magnitude is not going to change. So using only the first thing, that the direction does not change, we could say that the motion happens in a plane. Okay, the motion will be planar. This followed only from the direction. Then when we imposed, or we could utilize the constancy of the magnitude of L in writing down the following. Okay, that's the angular momentum which will be constant. Okay, and then we could also show that for a central force field, the Kepler's second law holds true. Okay, and then yeah, okay, let's proceed from here. I think let me see here. Yeah, it's here, it's already, we have talked, so I can just write down. So now let's continue with today's next steps. Now, because the motion is happening in a plane, which I have established based on the conservation of angular momentum, I can write down the Lagrangian of the system to be the following. So I have L. Now this half mu r dot square, this r is because it is going to be in a plane. I can write this as half mu. I'm writing in now polar coordinates, r dot square, where r is the radial coordinate, and then I should have a term coming from the theta coordinate, which is half mu r square theta dot square, and then you have the potential energy term. Now from here we can immediately write down the equations of motion. So let's write down equation of motion for the r coordinate. Okay, so we have to calculate d over dt del L over del r dot minus del L over del R, and this will be 0. So if you calculate these, you will find the following. So you get del L over del R dot will give you a mu R dot. It gives a factor of 2 which cancels here. Okay, and when you take a d over dt, it gives you mu R double dot. Then you have del L over del R, and both these two terms have R dependence. So from here you will get, so you have a minus which brings a minus here. R, because it's square, it gives a 2. 2 cancels. You have mu R theta dot square. Okay. Then the minus sign will cancel this minus sign, and you'll get a derivative of u. Okay, I can write du over dr instead of partial derivative as well, because u depends only on r. So there is no distinction between a partial derivative and a total derivative here. Anyway, so now we can substitute what we had for theta, this equation, okay, in here, and obtain the following. So we substitute, and we get mu R double dot minus L square over mu R cube plus delta U over delta R equal to 0. Okay, so I have removed the theta dot from this equation of motion, and now you see this is purely a one-dimensional equation of motions. This is a equation of motion of a system with 1 degree of freedom, and that is only R. Okay, the real system is still moving in a plane, so it is described by theta. But if you look at the R coordinate, it is like a one-dimensional system. Okay, and if you have we have already talked about one-dimensional systems and how to solve them in general. So we can repeat the same steps, and if you recall, it's easier to start with the first integral, which gives you the energy. Okay, and from there you can make several observations, and that is what I'm going to do now. Okay, and this is exactly what we did when we were talking about one-dimensional systems. Okay, so let's use conservation of energy. Okay, and what the conservation of energy says, it is that the kinetic energy plus the potential energy is equal to the total energy, and the kinetic energy here is half mu R dot square. But now I want to write it using the radial and polar coordinates, and I also want to use this thing, this fact, so I can write half mu R dot square, okay, plus this piece. See, this entire thing is the kinetic energy, right? So that thing, and I substitute for theta dot to be this piece. Okay, so I get half mu R dot square, and maybe I should write half mu R square theta dot square plus U of R is the total energy, and this is a constant, as I have repeatedly said that this is determined by the initial conditions. Now this piece is equal to half L square over mu R square, this term. So with that I can write the following. I can write my equation of energy conservation in the following manner. So I write half mu R dot square plus half L square over mu r square plus U of r is equal to the total energy. Again, as you, sorry, it should be dot square. This is the centrifugal term here. Now I will define these two, this sum, to be U effective. Okay, I call it the effective potential. Okay, so we have, you understand, right, why I call it U effective, because effectively the potential now is the sum of these two and not just U, if you look it from the point of view of the coordinate r. Okay, that's why I give it a name U effective. And good, so we know what we should do to analyze this problem. We remember last time when we were talking about a one-dimensional system, we plotted U of r. Now in case of U of r, we have U effective of r, and here you have r. And in general, your potential could be anything like this. That's the most general thing that can happen. It could have some minimum somewhere a maximum, and it could keep decreasing and go to zero as it goes to infinity. It could keep increasing somewhere in some region. Okay, so these are the most general features that can be present in the U effective of r, and we can now immediately see what are the possibilities that can happen. One is that your system is somewhere here, okay, meaning your energy of your system is such that your particle mu is here, okay, in the one-dimensional picture which we have, which would mean that the radius, the radius or the separation of this particle mu from the origin remains fixed. So the particle always stays here, okay, which would mean that the particle is going to move in a circular path, right? See, the theta is still going to change with time. Our theta dot was not zero, it was a, let's go back here. So you had a non-zero theta dot, so theta is going to change with time. So the particle is moving in plane with theta changing, but its radius never changes, which means it's going to move in a circle. Okay, so that's one possibility that can happen. Then what you can have is that you start your particle somewhere here, and it comes, let's say the particle has energy equal to this value. If your particle has energy this much, then if it has started from this direction, it is coming, it will hit the turning point and return back, and it will go to infinity and would never return again. Okay, that's one other possibility. If the energy of the system is somewhere here, you know what will happen, it will keep oscillating back and forth in here, and this oscillation is in the r. Okay, but while r is shuttling back and forth between in this region, the theta is still changing. Okay, so your particle is moving in plane with theta changing, and the radius is also changing with time. Okay, so this is another possibility that can happen. So let me write down. One possibility is that r remains fixed, which would mean that the mu is in a circular orbit. Is in a circular path. Okay, or the r may oscillate back and forth . But this does not mean that particle is moving in a line. It just means that in the r direction it is its r value is increasing and decreasing with time, but at the same time it is also moving in the theta direction. Okay, so it's not just an oscillation in one dimension. That's not the case. And third is r may keep increasing with time. May keep increasing with time after it has hit a turning point. Which was the case here for this one. Okay, and this is what in general will happen. Now, in order that we say more, we need to know the form of the potential. Okay, and then we can analyze the motion in more detail. So we are immediately faced with asking what are the different central potentials that are possible. Well, there is an infinity of potentials that we can write, but some of them are fairly simple and common. So you could have a central potential which looks like half k r square. Now this is your Hooke's law, which holds true for small displacements in general, but let's say I say that this holds true for all r. Okay, clearly it's an unphysical situation because as r is increasing, the potential energy will become infinite. Okay, it will have infinite energy, so it's not a physical situation, but as far as mathematical function is concerned, this is good. So this is our Hooke's law. Okay, and this is spherically symmetric potential now. So it's a spherically symmetric oscillator. Then you can think of inverse square laws. So where the forces are decreasing as 1 over r square, which means that the potential is decreasing as 1 over r. Okay, this will correspond to, for example, gravitational potential or Coulomb potential. Then you may think that, okay, instead of having an r here, I can think of a higher power of r below. Okay, and you may ask what happens in those cases. Another, I'm just listing down a few examples so that we keep in mind that there are several different central potentials that can be imagined. So you can have a k over r, which is same as the inverse square law. But the inverse square law, you see, this force dies off very slowly, so it can be felt at very long distances. But let's say for some reason I want to have a force which for small distances is more like inverse square law, but as the distance increases, it dies off very fast. So you can supply a exponential damping here like this, where a will have the dimension of r. Okay, and you will see that this cuts off the force very fast. So what you can do is you can compare this force with that force, okay, and ask how much smaller this one is if you go to, let's say, r equal to 10 times a. See, a is a length scale in this problem, right? So let's say you are 10 times at a distance 10 times a, then you compare how much smaller this potential is compared to this. This will give you a quick idea of why we say that this potential cuts off very fast as you go away from a at a larger distance. Okay, so these are some of the examples of potential that are possible, and you can construct any combination of these and several others. You can create maximum and minimum. You can create a central potential which has maximum and minima also. So there are lots of possibilities. Okay, so let's next. Yeah. Okay, that's fine. Now, before I start discussing one of these potentials, which will be the inverse square law basically, I want to talk a little bit about how we prepare the system. Okay, I mean, if it is in your hands. So or equivalently the initial conditions. So either you prepare or it got prepared. Either way, you have some set of initial conditions. Okay, so let's say we are looking at this one body problem to which we have reduced our two body problem. Okay, and I want to have my system to have a total energy E, some number which I choose. Okay, so the situation is this: we have a plane in which the particle will be moving, and clearly I have chosen a plane, which means that my angular momentum will be in this direction, some L. I have not chosen the L yet, but I know that this will the direction I have chosen. Okay, and let's say this is the origin O, where r is equal to 0, and let's say I want to start here. Okay, some point r, let's call it r naught. Okay, and I want my system to have a total energy E. Now if it is here, it will have some potential energy U of r0, right? Now if I want to have this number E as the total energy of the system, and I am saying that I am going to start my particle here, it already has a potential energy U of r0. Okay, and this difference gives me half mu r dot square. Okay, so pay attention, I have written a r vector, not just r dot. Okay, and this at r0. Okay, so which means that I know, or I can calculate from here, with what velocity I should fire the particle at r0. Okay, so if I calculate this, find the number, the velocity from this, then I should fire my particle, okay, with the calculated amount of velocity. If I do so, then my system is going to have the total energy E which I wanted. But I have freedom in choosing the direction in which I fire the particle. So I could choose to fire it towards the origin, right? If I do so, the energy is still E, but the angular momentum will be 0. Or I may choose to fire it, okay, by giving it a small angle. Or I may choose to fire perpendicular to this radial direction. And in that case, I will have the maximum angular momentum that is possible with that velocity. Right? So, depending on in which direction you are going to fire, you will get whatever value of angular momentum consistent with that. So, in that manner, you can prepare your system to have whatever value E you want and whatever angular momentum you want. And anyway, by choosing this plane in which you are firing, you have already decided on the direction of the angular momentum. Okay, so given E, several possibilities are there for the magnitude of L, depending on at what angle you are firing it. Okay, that's good. Now, let me just write it. Depends on the angle at which you fire. Fire the particle mu. Okay, this is fine. Now you may ask, if I choose some value of the angular momentum that I want for my system, okay, so I want it to have some angular momentum L, what is the minimum energy or maximum energy that is allowed for this system? Okay, so we ask, if we want angular momentum to have value L, what is the minimum energy or maximum energy allowed? Okay, so E could be anything. I mean, the upper limit is not bounded, because even if you have very large energy, you may fire it very close. You can fire it almost in the direction of origin. If you do so, then you can make the angular momentum small. Okay, so that way you can offset the largeness of the energy to make small L. But the lower limit is, of course, there is a lower limit on the energy, and that is what we want to see how. So the lower limit is this. You have E, the total energy E is equal to half mu r dot square, not the vector, plus U effective. You remember U effective has two pieces. One is the potential energy of this interaction plus the centrifugal term, okay, coming from the motion in the theta direction. Let me just show you once more here. Okay, this is the U effective. And also note that this piece which is coming here is positive. It's always positive. Okay, but U of R, this could be negative also, because there may be attraction. Okay, so there is a L dependence in here in U effective, and let's say you have chosen some L. We want to know what is the minimum total energy that is allowed for the system to have. Okay, and clearly the minimum energy this can have is the minimum of this, provided I can put the R dot to be 0. Okay, so the E minimum, you get the E minimum to be equal to U effective minimum. Okay, so if your particle comes to not rest, because rest would mean that particle is not moving, but R dot equal to 0 does not necessarily mean that the particle is coming to rest. It just means that the particle has come to a turning point. Okay, let me emphasize this. So you see here, if the particle is, let's say, coming from this direction and going, when it reaches here, the R dot will be 0. Okay, because it has to turn now. But it does not mean that the particle has come to really at rest, because in the plane it will still have some theta dot non-zero. Okay, so these two are different things. So anyhow, the minimum energy that the particle can acquire is equal to the minimum value of U effective. Okay, it cannot go lower than that, because going lower than that would mean that this piece has to become negative, which is not possible, because it's a square of a real number which will be positive. Okay, so that's the constraint we have. Okay, now with this understanding, let's look at Kepler problem now, which is basically taking a inverse square law force, which is applicable for gravitational force, for example, and that's what we will study now. Okay, so let's write down U effective. U effective would be U of r. So U of r is now minus k over r. Okay, then you have the other term coming from centrifugal term, to mu L square over r square. Okay, I would encourage you to think why you have such a term. Okay, I mean, of course, mathematically it's all good that it is there, but you should develop a feeling for this term, that yes, indeed, you really see that it should be there. Okay, for example, you can imagine sitting on the I mean, one way to think will be to sit on the radial vector, and let's say you are the observer which is sitting on the radial vector which connects to the point mu. Okay, the particle mu, and you have been told that this particle mu is getting attracted towards the center via this thing. But as the particle is moving around, you will not see that this is really getting attracted by this force. Okay, you may see it having additional force, and that will be due to the fact that this thing is really moving in a circle. Moving in a plane. So imagine that this thing was moving in a circle. Okay, and you were sitting on that radial vector. Then what you will see is that even though you have been told that there is a force which is attracting it, that particle doesn't move anywhere. It stays exactly at the fixed distance away from you. So for you, nothing is happening. It's just staying there. Okay, and the reason is that actually it is moving, but it's the motion is in the theta direction. Okay, so from your point of view, you will think that there is another force which is balancing that that attraction towards the center. Okay, and that there is another fictitious force, and which is this one. Okay, so anyhow, that's our effective potential, and to say anything about the motion, we should draw a diagram like this for the Kepler problem. So the first thing you should ask is, are there any maxima or minima? So what is the structure of U effective? So first thing is, let's find, are there any extremum points? And if they are there, whether there is a minimum or a maximum, or if there are many maxima or many minima, or both kinds are present, that is what you should ask. So you can check immediately the following, that if you take the first derivative and equate to 0, you get a non-zero, I mean you do get a solution, and this happens at r naught equals L square over k mu. So there is a potential candidate for an extremum. Please check this. Then also let's calculate the second derivative to know the nature of it. So if you calculate this quantity at r equal to r naught, you will find that this turns out to be I hope it's correct, k to the 4 mu cube over L6. Yeah, it's correct, I think. L to the 6, which is greater than 0. Okay, your k is greater than 0. I should have written specified here. K is greater than 0. Anyway, mu is greater than 0. L is L square, so it's positive. You have L cube, so it will be positive. So this is a positive quantity, which means that at r naught you have a minimum. Okay, the other solution which you will find here corresponds to r equal to infinity. And of course, at r equal to infinity, you don't have any extremum. It's just, it's not a local extremum. It's just falling off to 0. Okay. So yeah, you have one and only one extremum, and that is a minimum in this case. So for L equal to 0, there is, see, in this derivation I have taken L to be non-zero. So for L not equal to 0, there is only one local extremum which is a minimum. Okay, very nice. Now you know that at a point r naught, which is this, you'll have a minimum. Then you know that your u effective goes to 0 asymptotically as r goes to infinity. Then we also know, what do we know? Yes, that as r goes towards 0, your potential will blow up, and it will blow up in the positive direction, because this will blow up faster than this one. Okay, so for very small r really towards 0, you can forget this one, and this one will be the one which will control the behavior of u effective. So this is the kind of graph you expect for u effective for the Kepler problem. Okay, before that I should say something more. I should also give you an exercise, trivial, that find out what is the value of u effective at r equal to r naught, where the minimum is located. So u effective at r0 is equal to minus half k square mu over L square, which is negative. Okay, so now I know quite a lot. So let's say this is r naught. Let's say this is the value of u effective at this point, which is negative. That's why I've chosen this point to be here. And then it goes asymptotically to 0, because at r goes to infinity, this goes to 0. So I should have something like this. The slope should be 0 here. Okay, it should go to 0. Not looking very nice. Let me do it again. Okay, looks better. Oh. anyhow, and then it blows up. Okay, so your y-axis is U effective, this is R, and that's the effective potential that you have. Now our task is to analyze the motion of the problem, motion of this particle mu in this potential. Okay, that's what we will take up next.